Good day, ladies and gentlemen. We are looking at the quantum mechanical description of the electronic structure of an atom. So we're describing the electrons in an atom. And we've looked at the wave functions that are basically the orbitals in which electrons live. And we are considering the one electron system for the time being. And these are known as hydrogenic atoms. We now know how to put together a wave function for a one electron system, and remember we said one needs to find information using two different tables. You can obtain the spherical harmonics part of the wave function from table 9.3 in your data sheet, and the radial wave function part from table 10.1 in your data sheet. You multiply the two and that gives you the atomic wave function, or basically the orbital, depending on the quantum numbers NL and L and ML. So you can at this stage construct any wave function. Now we are also interested in answering the question, well, where is the electron? So that has to do with the probability density. Now, we know at this stage that if the wave function is psi, the square of the wave function gives us probability. But in the case of an atom, the story is a bit more complex. Because we have different variables, we have an angular part and a radial part. What we actually have to do if we want to determine probability is to determine something called probability density. And we're not going to go into the details as to why the regular probability doesn't work. You can read up about that in Atkins or on the web if you're interested in that. So we're just going to assume that probability, the typical square of the wave function, doesn't work. What you need to do is you have to calculate probability density. So probability density is given by this symbol, P as a function of R, and we define that as or at a specific radius. So how do you calculate probability density? Well, probability density is the square of the radial wave function, and remember this we obtained from table 10.1, and you just multiply that square by r squared, which is the square of the radius. So you can easily get the probability density. So it's straightforward to obtain that. Now this PR also has a different name. It's called the radial distribution function. And if you multiply that by a small distance dr, it gives you the probability of finding the electron in a spherical shell with a thickness dr at the radius r. So let's say there you have the nucleus. Then you draw at a radius r a very thin shell. So that's your probe that has a thickness dr. So what is the probability of finding the electron somewhere at that distance? So in this case your probe is basically a shell that you can make larger or smaller depending on r. And that is why we have to define it a bit differently, because our volume probe is a bit different. So let's look at the radial distribution function for a 1s orbital. So there's our formula for radial distribution function. And remember that you get from the data sheet Now for a 1s orbital, well, your table tells you 1s, but you also know for a 1s orbital n is 1 and L is 0. So there is the radial distribution function that we want, but we need to square that. So you can see what will happen to the exponents. That will be to the power 3, and that will be to the power minus rho. So that becomes 2 squared becomes 4, z to the power 3 over a. And you can then go one step further to substitute rho. Minus 2z r divided by a0. Now if we look at this equation, what can we say about the radial distribution function, so the probability of the 1s orbital? Because r squared, so this part, is 0 at an r value of 0. At the nucleus, the probability is 0. And remember, we've done many calculations where we've seen that the highest probability of finding an electron is at the nucleus. And remember, I kept telling you that this is not the full story. Why was it not the full story? Because we calculated the probability incorrectly. We used this. And now that we are doing it properly, using the radial distribution function, at last we get a sensible answer. Because we cannot find the electron at the nucleus, because then all the atoms in the world will collapse. So at the nucleus, the probability of finding the electron is 0. And then very far from the nucleus, as r goes to infinity, the probability will also go to 0 because of this exponential term. E to the minus r goes to 0 as r goes to infinity. Which makes sense, because the electron will not be an infinite distance from the nucleus. And then this r squared term and the exponential factor together has the effect that this probability passes through a maximum and then goes to 0 again. So it starts at 0, goes through a maximum, and goes back to 0 again. So this is the probability density, or the radial distribution function, for the 1s orbital. And you should be able to get this for any orbital. So if we plot the radial distribution function for a 1s orbital in a hydrogen atom specifically, this is what it looks like. At 0 and at r equal to infinity, it goes to 0 and it goes through a maximum. And this maximum is actually equal to the Bohr radius. So it's the most probable radius at which the electron will be found. And remember, how do you find that maximum? The maximum of any function is where the first derivative, or the slope, is equal to 0. So you can actually find that r value, which is of course the distance at which you will most probably find that electron from the nucleus. Okay, so let's have a look at an example. Now the mathematics is a little bit beyond what you need to know for this course, but I'm going to give you an equation and we're just going to look at how to interpret this. Calculate the most probable radius at which an electron will be found when it occupies a 1s orbital of a hydrogenic atom of atomic number Z, and tabulate the values for the 1 electron species from hydrogen to neon 9+. So basically what we want is we want to find a radius where the radial distribution function of the 1s orbital has a maximum. And that is where this slope So the first derivative is equal to 0 because that will give us that maximum. So the r, that radius, is what we want. And if more than one maximum is present, you choose the one with the greatest amplitude, which is typically the outermost one. So the radial distribution function we have just obtained. You know how to do that. And I'm just going to give you the first derivative of that. You don't have to know how to find that. Okay, now how do we get this function to go to 0? Because we're interested in where this is 0. Well, basically, when this term is equal to that term, everything in this block will be 0. So basically, with 2r is equal to 2zr squared over a0, then this function will go to 0. So this function is 0 when the term in brackets is 0, so in 2r. And when you rearrange this, you will find that it's equal to r, where r is equal to a0 over z. Okay, and z we have, it's 1 for hydrogen, 2 for helium, etc. And a0 we have the Bohr radius, so we can calculate the most probable radius for each different element because the z changes for each element. And what you'll notice is that these values decrease the radius the higher the nuclear charge, which makes sense. 52 picometers, 26, 17, 13, because we're talking about Coulombic interactions. So if you have a small positive charge, the attraction to the electron will be fairly low, but if you have a very high positive charge, the electron will be pulled closer to the nucleus. But there's still a centrifugal force that ensures that no collapse occurs. So the 1s orbital is drawn towards the nucleus as the nuclear charge increases. So the take-home message is that we use radial distribution function to get probabilities when we are dealing with an atom, in this case specifically a hydrogenic atom. Okay, I now want to share with you a magazine article that appeared in a Popular Physics magazine. And you might not be able to see this text, but it's just something interesting related to what we are working on at the moment. Now, if you want to go and Google and find this article, the title of the article is Quantum Microscope Peers into the Hydrogen Atom. And what it says here is the first direct observation of the orbital structure of an excited hydrogen atom has been made by an international team of researchers. The observation was made using a newly developed quantum microscope, which uses photoionization microscopy to visualize the structure directly. So the wave function is a central tenet of quantum theory. Put simply, it contains the maximum knowledge that's available about the state of a quantum system. More specifically, the wave function is the solution to the Schrödinger equation. The square of the wave function describes the probability of where exactly a particle might be located at a given time. Although it features prominently in quantum theory, directly measuring or observing the wave function is no easy task, as any direct observation destroys the wave function before it can be fully observed. So in the past, Rydberg wave packet experiments have tried to observe the wave function using ultrafast laser pulses. In these experiments, the atoms are in a superposition of the highly excited Rydberg states, and these experiments show that the periodic electron orbitals around the nuclei are described by coherent superpositions of quantum mechanical states. The wave functions of each of these states is a standing wave. We've seen this before with a nodal pattern. We've talked about nodes. A node is where there is zero probability of finding an electron, and it reflects the quantum number of the states. We've talked about that. While previous experiments have attempted to capture the elusive wave function or the nodal pattern, the methods used were not successful. Direct observations of the nodal structure of a single atom being most difficult to achieve. Now, what these scientists managed to do is they managed to use photoionization microscopy to obtain the nodal structure of the electronic orbitals of a hydrogen atom placed in a static electric field. Now, you can in your own time read more about this, but I just want to share with you the amazing observations that they made. And these pictures may not be very clear, but what they were actually able to see is in the different excited states, you can see the nodes appearing. And this is basically what we've just described. So if you look at the radial distribution functions, so if you start in the middle and you move in a specific direction, you go through areas of high probability, lower probability, high probability, and these have been calculated. That's experimental. And there is such a good correspondence between calculated and experimental results. So these are wave functions or probabilities that they are actually seeing for the hydrogen atom, for the different states. And my apologies, these colors don't show that well, but you can actually see nodes, and you can see so at the nodes you will have a zero probability of finding electrons in the hydrogen atom. So this is absolutely amazing that one can see the probability densities in an atom like this, and see it experimentally and visualize it. Okay, now we go back to other orbitals and wave functions. We've talked about the s orbitals. Now we go to the p orbitals. Now for the p orbitals, L is equal to 1, ml minus 1, 0, 1. Remember, ml is determined by 1, the number of values for ml. So in this case there are 3 p orbitals, and they differ in the orbital angular momentum about a specific axis. So the J, Z values are different. That's why we have 3 different p orbitals. However, the magnitude of angular momentum is the same. Why? Remember, we said that is only determined by L, and L is the same for all 3 orbitals. So if we have a look at the wave functions for the p orbitals, you can also construct them from the information given in the 2 tables. So for the 2p orbital with ml equal to 0, you can find the radial part in table 10.1 and the angular part in table 9.3. So from this you can construct any wave function. We know what the p orbitals look like. And again, go and have a look and see if you can get the wave functions for the 2 p orbitals with ml equal to plus or minus 1. And then we can do the same for the d orbitals. You know what the d orbitals look like. In this case, they differ in angular momentum about the z-axis, but the magnitude of the angular momentum is the same for all the different d orbitals.